Okay, so we're going to work on 2.1, which is the derivative. And that's just going to be an extension of the tangent line problem with a little bit of the limit put together. So let's take a look at this originally. Let's take a look at the tangent line problem. So I'll go ahead here and we'll do a set of axes here. And we'll go here. And I'll draw, something, any arbitrary function, but I'm going to draw something that's easier for me to play with. So some kind of function like this. Here's my x-axis. This is my y-axis, or f of x. So we'll start with an arbitrary point right here, let's say. And what I'll do is I'll arbitrarily draw a secant line. We talked about that. So here's a secant line. And when I draw the secant line, I will label this x, and this is y, or f of x over here. So that's my, I will call it point 1. We'll be very clear about that. So point 1 will be x comma f of x. So we have a point on this function f, and we have 2 points on the secant line. So point 2 is going to be arbitrarily away from x. In this case, I'll say it's arbitrarily over here. So that distance we will say is some arbitrarily distance of delta x. So that means this point here would be best labeled as x plus some delta x. So that's the part of that point. And over here, if we were to put that x plus delta x in the function, that would give us that second component of that point, y. Do apologize for that. So point 2 will be x plus delta x, and then f of x plus delta x. So those are our points, and we'll do the slope of the secant line. So we'll do the slope of the secant line, which would just be the slope of a regular line, which is y2 minus y1 over x2 minus x1. And if we work that out, that'll be f of x plus delta x minus f of x all over x plus delta x minus x. And if we simplify that just a bit, that's f of x plus delta x minus f of x over x minus x, just delta x. So there's what we did before. We've got the slope of the secant line. Now, if we arbitrarily start making this delta x small, we talked about that before, we would get actually a tangent line. So we can keep doing this, making this delta x smaller and smaller and smaller until we have a single value going through this line. And then what we really do, and this time, in this case, that actually, the way I've drawn it, it might actually be right here. But that would give us sort of this line here. And that would be the tangent line. And what we're doing here actually is we're making that delta x smaller and smaller and smaller. So we would start here, do a tangent line there, there, and eventually we get here. So that's how we're going to state it, and we're going to actually define it that way when we define the derivative. So that's what we're going to do. We're going to actually go ahead and do that definition. And this is definition of a derivative. And often we say it's definition of the derivative as a limit, because that's exactly what we're going to do here. So we're going to just take a look at that. What we're looking for is really the slope of the tangent line exactly. So what we're going to do is we're going to say, well, we take the slope of the tangent line, which we'll start with as f of x plus delta x minus f of x over delta x. We take the limit of this, and now we're going to let delta x go to 0. And this is the definition of the derivative, which we are going to use a little notation of this f prime of x. That's not so obvious there. We'll redo that there. So f prime of x. We write it that way. That's the derivative. So this is the definition of derivative's limit. You're going to need to know that because we'll ask, direct questions. Use the definition of derivative to find the limit or that derivative of a particular function at a particular point, perhaps. So this is what we get. This is basically the slope of the tangent line to the graph at exactly the point that we want. So this is going to be the slope to the tangent line at that exact point of x. Often you'll see, and we'll see it written, is we'll talk about the slope of the tangent line at x equals c, particularly, and you'll see that in your textbook, and that actually be written slightly differently. So that's f prime of c. That value is going to be the limit as delta x goes to 0, and at c it'll still be c plus that delta x minus f of c, whoops, over delta x. So you'll see it written as that, and the difference here is just the c instead of the x. And that's really great because what we're doing here is any function that we have, we can go back here, we're actually getting that slope exactly at that tangent point. And it's going to be specific to the function. And so as long as we can figure that out, we can do that for any function. So we can do a particular example. And we'll call this example 1. And we'll say, let's say we have the function f of x is equal to x squared minus 1. And we want to find the derivative of that in general, and maybe the derivative specific of that at a value. Let's say, let's find the slope of the tangent line at 2. We'll write it that. So the slope of tangent line at x equals 2. And we'll use our definition of derivative because at this point that's what we've got. So when we do that, we'll have to write our definition down. So we do definition of a derivative. So that'll be f prime of, and I'll use the c version of that, equals f of c plus delta x minus f of c all over delta x, the limit of as x delta x goes to 0. So that's our definition. So we're going to need a couple of things in there. We're going to need f of c. Well, f of c particularly is going to be c squared minus 1. And f of c plus delta x, that's going to be c plus delta x squared minus 1. Now you have to be careful about that. That'll be c squared plus 2c delta x plus delta x squared minus 1. So we work those two values out, we put them in. So we get this is equal to the limit as delta x goes to 0. And for f of c plus delta x, I have that worked out part, c squared plus 2c delta x plus delta x squared minus 1 minus f of c. Be careful with the brackets here. That's minus c squared minus 1 all over delta x. And we'll take a look at that. That's going to be equal to the limit as delta x goes to 0. And we'll see what works out. We have a c squared here and a c squared here. They cancel. We have 2c delta x plus delta x squared. The 1 minus minus 1 cancels as well. So we're just left with that part. Here we could factor out the delta x, 2c plus delta x. We're going to need to factor it out. If we tried to do this limit, we'd get 0 over 0, so we'd have something that we couldn't evaluate. We do this, and we get to the point where we have 2c plus delta x. And whoops. Two c plus delta. Whoops. Go back here. Forgot the limit part. Sorry. So we'll continue that. We have equals to the limit as delta x goes to 0 of 2c plus delta x. And now when we let delta x go to 0, this part of the limit, we simply get 2c. So that actually gives us a derivative in general. And now if I want f of c in this case is equal to 2, I'll put 2 in there. So f of 2 is 2, I get 4. So in this case, what I get is that the tangent line is going to have a slope of 4. And that's a pretty interesting thing. If I was to take my calculator out, let's see here, I'll pull that up. Let's actually pull up a decimals. This is a nice graphing calculator here, and if I put the function that I had, which was x squared minus 1, and I look at the value 2, which is precisely right here, so I can see that value right here, and I drew the slope with an intercept of that. So let's see, if I drew 4x, that's a function with slope 4, and let's say if I move that over, for x. Try to be precise here. There we go. So I was just playing with it. I can see that at 2, I have that tangent line right precisely here at the point 2, 3, and I drew that tangent line. Later on, we'll see where I came up with this equation. But you can see that that blue tangent line, that's where the slope is equal to 4. And you could see that slope is right here, the 4x of the blue one. So that's pretty interesting. We're able to do that quite quickly and easily using the definition of the derivative. And we can do that with even more complicated functions. So I'll do that with a different example. So if I was to do, for example, y is equal to f of x is equal to the square root of x. Now that's a little more challenging. Notice we have a limited domain and range of this function. So if I was to, graph this as a family of functions, we know that the domain and range here, the domain is going to be from 0 to positive infinity. The range is going to be 0 to positive infinity. So we have a limited area here, but given that area where the function is well defined, we're going to go ahead and find, let's say, the equation of the tangent line at any point. So we can do that by doing the definition of derivative. So again, I'll write down the definition of derivative. that is f prime of x is equal to the limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. In this case, I'm not going to use the c version. I'm going to use the x version. You'll see why in a minute. It's just a lot easier for me to deal with. So that's my definition of the derivative. I'm going to go ahead and work that out. So in this case, I have to be a little more cautious. So I'm going to have that equal to the limit as delta x goes to 0. And my f of x plus delta x is literally going to be putting x plus delta x into the square root. So x plus delta x, that will give me the square root of x plus delta x. So that's what I'm going to get over here. And over here, it's just going to be minus f of x, which is just the delta x, the square root of x over delta x. Now, once again, if I go ahead and do my limit, if I do my limit as direct substitution, which I really should, so I substitute delta x for 0, so I'll get x plus 0 here minus square root of x over 0. I will get 0 over 0, which is, remember, the indeterminate form. That tells me that I got to do something else. In this case, I'm actually going to have to do a little manipulation. When you have square roots, the best way to manipulate square roots is to multiply by the conjugate. Remember? Conjugate. The conjugate of the square root of x plus delta x minus delta of x is the positive version of it. The conjugate is going to be x plus delta x plus the square root of x. So we're going to use the conjugate, the same expression but with a plus sign, and we're going to multiply top and bottom, numerator and denominator. So we'll take the x plus delta x minus the square root of x, and we're going to multiply top and bottom by the square root of x plus delta x plus the square root of x over square root of x plus delta x plus square root of x, and see what we get. When we do that in the numerator, notice each step I have to carefully write the limit out. Don't want to lose that. So here I have the difference multiplying. So I have a minus b, a plus b, a difference. So it's really going to be, if I complete it, it's going to be the square of the first. So it's going to be the square of x plus delta x minus the square of the second, right? The middle term will fall out, and the square of the second will be the square root of x squared. On the bottom, it will be the square root of x times x plus delta x plus the square root of x. In the numerator, I will have, let's see, x plus delta x squared will just be x plus delta x. Over here, I'll have just the square root of x squared, which is x, over square root of delta x, and I still have the square root of x plus delta x plus the square root of x in the denominator. Now in the numerator, the x's cancel, so I have the delta x over delta x. That also cancels. So I am going to be able to reduce this down to having simply 1 on the top, and in the denominator, I'll have the square root of x plus delta x plus the square root of x. And in this case, that's nice, because if I take the limit now, I let delta x go to 0, I will have 1 over square root of x plus the square root of x, or 1 over 2 root x. So that ultimately is my derivative. I'll call it f prime of x. And notice when I write it like this instead of with the c, my statement becomes a little more generalized. This is the equation of the tangent line at any point x where we have a definition. So we can see we can use that on the domain. And remember, we have to be careful here. Our domain was positive values here. So I can do, for example, f prime of 1, which would be 1 over 2, the square root of 1, which would be 1/2. So once again, I can go back to my Desmos and play with this. I can go here and do the square root. I'm going to do x to the 0.5 here. That'll be the easiest way to do the square root. Whoops, I get that. Yes, 0.5. That's the square root part there. My slope was 1/2, so it's going to be 0.5 x, and I need to move that up a little bit, maybe +1, no, 0.5, there we go. So that's my tangent line at 1, 1, and you can see I've got the slope of the tangent line. So that kind of begs the question, that question right there is, how am I finding these tangent lines? It's the second time I've done that. So I'm going to actually go ahead and do that here. Notice I have the slope of the tangent line right here. So that is the slope. And I also am doing this at the point x is equal to 1. And if I do f of 1, not f prime of 1, f of 1, that's the square root of 1, which is 1. So essentially, I have the slope and I have a point. Well, if you remember our y equals mx plus b format, what I have here is I have the slope. And now if I do step 2, I have the point. I'll replace y for 1, and then x for 1. And if I do that, I'll have 1 minus 1/2 equals to b. So what I'll have is y is equal to 1/2 x plus 1/2. So that's exactly what I typed in here into Desmos, is I typed that into my function. So that allows me to come up with that equation that I'm using here in Desmos to show you the second equation. I use 1/2 x plus 1/2, and I can come up with the equation of the tangent line. So that means I actually have 2 questions I can answer. I can find the tangent line, or the derivative at any point of a function, even a function as unusual as square root of x, and I can find the equation of the tangent line to that function by finding this value out. I have the point that I can work out. I have the slope. So that actually introduces 2 things that I can do. The derivative with the definition of the derivative and the tangent line question. I can actually find the tangent line equation now very quickly. So this process is kind of long drawn out. Obviously, if the function becomes a little more complicated, we're going to have a little more problem to go on with it. Let's see. 2 other things that we're going to deal with right away related to that are differentiability and continuity. So when we take a look at our function here, we can see a lot of things going on. But you can see that this function, as long as we can find the derivative of this function, it seems that we can also say that the function is continuous. Notice if I go up here and I do the equation of the tangent line, I can work that out. I can do that up here. So as long as my function is differentiable, okay, then I can say that it's also continuous. And remember, our definition of continuity was really kind of simple. So we'll go back to that real quick. We said that a function was continuous if it had what? If it has a couple of things, right? That first of all, that f of c at that value existed. That secondly, that the limit as x goes to c of f of x exists. And the third thing, the third point, is that literally that f of c is equal to that value as the limit goes towards it. Okay. In a graphical sort of sense, okay, it means that if I had a function and I had a c value, literally it means that f of c exists. So there's a point on the function of that graph. The limit was saying, well, if I approach the value c, no matter from where, that it would approach the limit value. And that meant it approached it from either side. So this is our idea of continuity. If that's the case, then we can say, look at it from a differentiability point of view. If I take this value and find the derivative at that point, then it's going to give me the same thing, because if I can find the derivative, remember the derivative means that I'm doing the limit as x approaches this delta x, right? Or as delta x, I should say, goes to 0, really. So I'm actually approaching it from either side. So I'm approaching the function. And when I'm doing that, I'm finding out its slope. Well, that certainly implies that it also has a function value there. So we can say that continuity, or I should say differentiability, implies continuity. Now, what is not the case is continuity does not imply differentiability. So the other point, so continuous does not necessarily imply differentiability. And we can see that simply by doing an absolute value function. So an absolute value function, you can see, certainly is continuous. It's defined in this case for all x element of real numbers, or from infinity to infinity. If you remember that, we see we have continuity there. But differentiability is not going to be definable at a point. When we try to draw that tangent line to a sharp point, that's not going to work, because the tangent line, it's going to be almost, do I draw it here? Do I draw it here? Do I draw it there? So what's missing here is as I approach it, the function is not going to have a derivative. So you want to be careful about that. We can do the next example. We can just look at a function that has a missing point. So a function that has a missing point. So here's a function that's defined everywhere. We said this one was not continuous. And notice this one is also not differentiable. But we can go the other way around. We can say this one does not have a derivative if you want. So that's one. The last example I'm going to do with differentiability and continuity is going to be something like one of our values that we had before. For example, if we had an asymptotic behaving function, a function that was looking like this is also going to be an example where we have both problems. And this one is very easy to see. Obviously, if I try to draw a tangent line here, I'm going to fail. So this one is not differentiable, and it is also not continuous. So you need to be careful. The one solid thing is, if you can find a derivative of the point, you can also say it's continuous. And that's one of the things we might do later on. For example, we'll go right back here. If you look at f of x is equal to the square root of x, and we stick on the domain 0 to positive infinity, if we look at f prime of x for that, which is 1 over 2 square root of x, notice that is definable, and the domain 0 to positive infinity. The only problem might have been 0, but we took that out. Therefore, this is differentiable on the domain, on 0 to positive infinity. Therefore, it is also continuous on the domain. And this is exactly how we'd use that differentiable implies continuity, is that we actually take the positive feature or characteristic of differentiable across a large number of values, and we can assume continuity without worrying about it. And when you draw that function, it's really obvious this is a continuous function. So that kind of gives you the derivative and the tangent line problem, and we can go on and work on a couple of more of these. There's going to be different ways of doing these. As the functions get larger, you're going to have to do a little more work. So I'm going to do one more example of that, and do it with a cube function. So we're going to do f of x equals x cubed, and we'll find the derivative of that. So we'll do the same thing. We'll write the definition of the derivative. F prime of x is equal to, well, as usual, the limit as delta x goes to 0. Obviously, I think in the future we're going to want to find a shortcut to this, but we'll go ahead. X cubed, so we'll have to be careful. X cubed, if f of x is x cubed, so our definition is going to be f of x plus delta x minus f of x all over delta x. So we'll have to take x plus delta x in there, so x plus delta x cubed. Well, that's going to be fun. So that part is going to be a little longer to write, but let's go ahead and do that. F of x plus delta x is going to be x plus delta x cubed minus f of x, just x cubed, all over delta x. If you're noticing kind of a pattern here, every time we do this, we end up removing the entire f of x part. It gets eliminated. So that's kind of a hint. That's going to kind of happen every time. So delta x goes to 0. So we're going to do this expansion x cubed plus 3x squared delta x plus 3x delta x cubed plus delta x cubed minus x cubed. So our expansion is, meaningful, large, but we can do it. Here is going to be the limit. Notice I keep writing that limit out. If I do x cubed, notice here the x cubed, I talked about that. That always cancels out. I'm just left with 3x squared delta x plus 3x delta x. This should be a square. My bad. Plus delta x cubed over delta x. If we substitute in this, it's 0 over 0, so we have to do something else. So it's indeterminate. So I'm going to have to take a delta x out of the numerator. So that'll be 3x squared. Notice there'll be one part left here and two parts left here. That's fine with me. We still have the limit as delta x goes to 0. And if we do that, the delta x's cancel out, which will be the limit as delta x goes to 0, and then I'll be left with 3x squared plus 3x delta x plus delta x squared. Notice if I put 0 in there, do a direct substitution, the only part that's going to be left is 3x squared. So that is interesting. And notice we've got the derivative. This is f prime of x at any value. X cubed is a polynomial. The domain is real numbers, and the range is all real numbers. And notice the derivative is a quadratic, which also has a full domain, but it is going to have a restrictive range. But that's the derivative.